Hi folks. So we're going to do a little bit of differential data flow programming today. I've been reading about some stuff online, so I thought I wanted to try this out. In particular, I've been looking at sequels with recursive construct, which is one of the ways to do iteration or recursion in a language like SQL. And with these examples, there are some cool programs that people wrote online, things like the Mandelbrot set, and what we're going to try today, which I thought would be a Sudoku solver. I haven't tried to write this before, so we're going to see how it looks. The rough plan is that there's probably going to be some fixed point iteration in Sudoku solving where we have a bunch of constraints, and the constraints sort of impose more constraints, and we develop up various bits of constraints, possibly finding, if we don't have to do any backtracking in the Sudoku problem, possibly finding a solution just in one go. But we'll also try to walk through, with time permitting, a backtracking solver as well, which isn't actually as complicated as it might sound. It just means, start guessing stuff, and that's actually not going to be so hard to write. Whether it works well is a totally different question, though. So I'm here in the Differential Dataflow repository, and I'm just going to open up a new example file here. It's just easy for me to sort of copy and paste some stuff. So like I might take the BFS example, which is all like super complicated and stuff, and I'll just save this as Sudoku. Sweet. And we're gonna tidy up. We don't need all of this nonsense here. This is all just, you don't even want to know. We are going to want to build a data flow. We might want some randomness. I'm not entirely sure. I'm not really sure how to generate random Sudoku instances. We're probably just going to copy some ultimately. One of the things that is meant to be sort of cool about this, though, is with the Sudoku board supplied as the input board supplied as data, as you potentially add and remove constraints, there might be some nice incremental update properties in terms of the solver incrementally telling you what are the new solutions that are available when you remove a constraint, or what solutions go away when you add a constraint. Or it might not work at all. We're gonna have to see. So let's see. I'm just gonna delete a bunch of stuff here so that we don't have to think too hard about what's going on. BFS, yeah, it's obviously not going to be BFS, but we might want to steal this and create a different helpful method that's going to do some stuff for us. So, okay, so some of you might not know what Sudoku is, and maybe you do. Bear with me. We're just going to all get on the same page. So Sudoku is this problem, sort of like a crossword puzzle type thing. Usually, it's sort of printed out in newspapers or books or whatever, and it's a 9x9 grid where in the grid cells you're supposed to place the numbers 1 through 9. Each of them occurs 9 times, and there are so the board is a 9x9 grid, should ultimately contain 1 through 9 each 9 times. There are some constraints, and these constraints are what sort of make the game interesting, or tickles your brain and causes you to think of it. So, for example, in each row, each number should appear exactly once. And the same is also true of each column. Should appear exactly once, and the same is also true for each 3x3 region. There are 9 3x3 regions that you can draw that don't overlap, and in each of those regions, the numbers 1 through 9 should each occur. Just gonna, the obvious one. So for any pedants out there who are like, oh, you could make lots of, no, it's just these sort of cardinal 3x3 regions, the ones that are sort of obvious, where you get by taking the grid positions and dividing by 3. So these constraints are helpful. They drive essentially the derivation of a solution from some initial constraints. Sorry, it's from some initial, let's say, placement of numbers. These constraints are going to force other numbers to either exist or not exist in certain other locations. Good tells. And I don't know a lot about Sudoku. So there's two types of derivations that I'm aware of. So first off, the existence of specific values rule out other values in the same row, call, and cell. There's probably a good term for the 3x3 region. I'm sure the Sudoku community has that. I'm not sure what to call it. Also, the absence of all but one value from a row, column, I guess, or a cell determines that value. So if we have 8 values in a row and one question mark, we should be able to figure out which the actual value of the question mark. And these two rules, possibly some other rules, but these two rules are meant to sort of drive derivation forward, help you reason about what might be where, given some constraints. Now, you might eventually get to a point where there's really nothing else. These rules don't apply anymore. You can't derive any further bits of information. In that case, you kind of have to start guessing. And I think Sudoku problems are typically rated by how many times you have to guess. So how much backtracking might be required. If these first two rules just apply, then it's really just an automatic process for you to go and solve all of them. But invariably, you'll get to the point where it's like this entry could be a 7 or a 4, we don't know. You try out 7, you see if that leads to contradictions down the road. If it does, you come back, you try to 4 instead. And it turns out this is going to be totally fine, I believe. Or sorry, we'll see. We'll see what happens. At the very least, there's a recursive SQL program that does this guessing for you in a not super complicated way, basically, where you just have a big long lit vector of all the places you might have to guess, and it just starts guessing them recursively, sort of iteratively, really, scribbling in values and continuing, and then throwing away rows if they have contradictions. We're not gonna start there because I don't think that's the most interesting thing to write. Also, just be transcription of what's already been written. So my idea is that we could model things in the following way. So before we actually start writing too much here, roots, graph. So just looking around at what we got probe handles. This is all a lot of mess. So I think we can have probe handle and input handle are things that we can import, and probably have already imported from right up there. Bother. We'll tidy this up. Tidy this up later. So I imagine one input essentially. Sorry, I should talk through what's going on here. We're writing a Rust program. Rust has some imports up at the top. You write a main function. Differential Dataflow is hosted inside Timely Dataflow, and Timely is something that you structure your programs by writing a closure, essentially, that you pass to this execute function. The closure, which we see over here, and basically the rest of the program, is going to tell each worker thread what to do. This is this sort of SPMD model, single program multiple data model, where a bunch of collaborative workers start up at the same time. They're running the same program, but they start with different data, and they're able to exchange data with each other, by which they get data parallelism and potentially can scale out. And I have no idea if, probably Sudoku doesn't actually require that from us. This is a bit more about, can we use the idioms in differential Dataflow to implement Sudoku derivation and potentially the backtracking, solving stuff too. All right, so in this closure, we're grabbing a timer because probably we're going to want to report how long various things took because we're very sensitive about that type of thing. The main thing though that we do, and we might do this, probably just end up doing this just once, is build a data flow graph. So this is the worker is ready to do some work. We can tell it, here's a computation we'd like you to construct and host potentially as the data change. So we're gonna build a computation that's going to do some Sudoku derivations, and then after we've done that, we're going to start supplying some inputs to it that are going to introduce constraints to the problem. So initially unconstrained, but then introduce some constraints. And hopefully what we'll see is the results of the computation will start to spill out, and they will describe, appealing, delightful solutions. Maybe if we start with some easy Sudoku problems, the answers will spill right out, and there'll be one solution, and we can feel very pleased with ourselves. Probably there'll be bugs, stuff like that. But let's create a new input here. So we're gonna have this is gonna be like the starts. So start input and start new collection. I'm just copying what we've had before, obviously. So this is gonna be where the initial values come from, and let's just make some notes about the types here. My guess is what we want to have is a value, a row, and a column. Just sort of making that up. But this is going to describe a particular location in the grid and the value that lives there. So grid of row call equals val. So we're going to start with this this collection, just this thing called start, which has a bunch of data in principle in it. Right, it doesn't quite yet, but we're going to write the computation as if it does, and we're going to start. We're going to try to write down some computation, something that can do some derivations about what we might possibly have. And my thinking about this is that what we might do is iteratively develop the set of possible val row call entries. So for any row call where val already exists, that's it. There are no other options. But initially, at least, for every row and column where val does not exist, we have 9 possible things that could live there, and we will I guess we'll initially populate those, and then we'll try to write a nice iterative bit of computation that will repeatedly reduce that set based on the constraints that we have. So let's think about doing that. We're essentially going to write something very similar to this structurally. So if we do start, and we make it Sudoku, great name, and all of this logic is going to do afterwards. We'll have to write some. I guess we'll comment it out for a moment. This is a standard pattern. If you want to see the results, you can supply a little flag, and if the flag is not set, we just delete all the results, so that the downstream data flow doesn't ever print anything. But let's just do this for the moment. So whatever comes back from the Sudoku thing, we'll consolidate it. That just means cancel out any pluses and minuses. So if we have a record and then we delete it, then we add it back in again, we reduce that down to just one occurrence. Print it out to the screen, and then probe the result so that we can know have we actually gone as far as we need to. I'm pretty sure we're not going to need any of this random stuff. So what we're going to need to write now is what do I just go like U8, U8, U8. This is super efficient, almost certainly unnecessary, but we're going to do it anyhow. Not really sure if there's a better. We'll see when we start to do this. Maybe we want U sizes there because we might need to use little arrays or something like that. All right, so this is standard let me break this up just a little bit so you can sort of see better. Us defining a method. The data structures in timely dataflow and differential dataflow are all generic with respect to some context in which they live, a scope. This is the same way that when you're writing a computer program, you have scopes. These collections also have scopes, and it behooves them to know what that is statically to make sure that you don't accidentally wire up a bunch of variables across different scopes. And we are going to take in I'll just actually steal this whole thing. We're going to take in this collection of starting constraints, and we're going to produce a result of just a collection of viable, possible output value row column locations. So from initial val row call, populate all row call with possible val. This uses, I call it purely optimistic reasoning. We're just gonna assume that we can go forward from our constraints and apply them, and does no guessing at all yet. And so what comes back might not actually be a valid solution, but it'll have reduced the space down substantially. And in fact, actually, if we wanted to, we could start from, I wonder if this makes any sense. We could start from a pre-expanded version of like all known locations. So you can imagine someone's actually pre-populated all the possibilities, and that would give us a method that we could sort of apply at any point, really. If we had done some other type of reasoning somewhere else, we could apply this again. It would reduce down the choices based on our reasoning. Yeah, let's do that. It means we're gonna have to write this logic somewhere that starts from a fixed set of constraints and without any constraints about absent rows and columns, and expands that out. We're gonna have to do that somewhere. It doesn't have to be here. So we're gonna change this candidates restrict based on constraints. Sweet. And we don't need all this crap. So great. So I think this isn't too complicated, though. Again, we're going to want to steal some of this sort of code. We have this starting collection, and I believe what we're going to want to do is iterate from it. And I think we've now stolen pretty much enough. Let me just delete all this. So we're going to want to iterate in the sense that we're going to start from this collection of candidate values at rows and columns, and we're going to repeatedly try to see if we can delete some things from that. We have two rules. Two classes of rules at least, right? One of them says if a row and a column have exactly one value that could possibly be there, that has the potential to remove a bunch of other that value from other rows, columns, and 3x3 cells. So let's just start by writing that rule out. So first, let's write a little bit of logic that tells us from all of these candidates which are the ones that correspond to well-determined locations. There's only one value at a particular location. I think the way to do that is we're going to take inner, we're going to map it. So we've got val row call. What we really want to do is go to row call. So we want to make row and column be the key, because row and column tell us, we want to collect together all the values at a particular row and column location. That's going to be an exciting thing to do, to reason about, is this the only thing there? So if we do that arrangement, so we put them into key value form, row, call, and then val, we can call the reduce method. And what reduce does, given a closure, we get access to a key, and two collections, the input values. So the key will be a pair of row and column, the input values, which will be the list, essentially sorted list of all the values that happen to be input there. And the output is something we need to populate. We need to put there any values we want to produce as outputs. And this doesn't have to be super complicated. I bet it's as simple as if input.len equals 1, output.push input dot clone, 1. So what we're saying here is if the input, the list of values, has length exactly 1, then we should grab that first element. What each of the things in input are a pair of value and count. So it's a value and how many times did we see it. We don't care about the multiplicity here. I mean, it'd be a bit weird if the value were something other than 1, but we don't get shown zeros. So let's just imagine it's going to be 1. We'll clone the value, put it down there, and then put a 1 as the associated value. So this goes through, and I believe this will be the collection of determined row call positions and the associated value there. And this is now going to exclude a whole bunch of locations. So let's write all this down. Let exclusions be, and I bet it's going to be 3 things, right? So we're going to do determined dot map. So for every determined dot flat map, for every row call val, we're going to want to produce well, all of the folks in that row, except for this row, should go away. So if we do, how are we counting these things? I guess we're starting at 1 because that's what you do in Sudoku, I think. So we do 1 dot dot 10, which will give us 1 up through 9. Dot, and I'm not sure that's a great way to not have I have no idea if this is the easiest way to write that. But sorry, what we're doing is we're taking all of the locations that we need to cross out. We don't want to cross out our own location though, obviously, because that's locked in. We could, I suppose, like we could cross out everything pretty much, and then put the determinants back in at the very end. Yeah, it might be a little cleaner. This is probably more idiomatic though, so let's, or it cleaves a little closer to what are we actually supposed to be doing. I get this nonsense out of the way. So for each of these rows, so this is going to be meant to be a row, we're going to map the row into our call, val. So so these are this is one of the cases, I suppose, and there's 3 of them. So let's just let this be exclusions row. And we're going to do 3 of these, exclusions call, which is going to take these same folks. We're going to do, instead over here, just to stay sane, C, call, we're going to take C, we're going to keep the row, but slot in the column that we're supposed to throw away. And now this gets a bit more complicated, this one over here. I mean, we want to do this thing where we take row and call. Oh, what a horrible mess. We're going to divide down, subtract 1, divide by 3, add 1. Oh, what are these people who don't use base 0 math make us sad. Okay, well let's try to write it at least. So we could also just make this be 0 dot dot, like 0 up to 8. That'd be super sad, but let's try to do it the Sudoku way. So for each, so we're gonna do 1 dot dot 4 flat map. So these are going to be the 3 different values, 1, 2, and 3. Actually, let's just write that. This is dumb. No, we need this. Sorry, it's going to write like a vec of 1, 2, 3, but it's going to do heap allocations each time, and we shouldn't do that. So this is going to be a candidate row. We're doing a flat map again inside here because we have to do 1 dot dot 4 again. Dot flat map. No, not flat map here, sorry. Dot map. It's going to be a C. Oh boy. Except before we do this, these iterator combinators are not quite the delightful programming experience you were promised, are they? Before we're going to map C to R comma C. Dot filter R comma C. Now we only want to cross out things that are we don't want to cross out row and call. So we are going to we don't want to cross out the specific location in the 3x3 grid that row and call are currently at. Delete this. People aren't confused. Great. So what's the logic for that? Let's see. We could do this a little differently, maybe. This is probably easier, actually. Yeah. So let's do let row off equals, and we've got our row is 1 up through 9. We're just going to try to find the 1, 4, or 7 where it starts. So I bet this is going to be 1 plus 3 times row minus 1 over 3. So all that we've done, we're trying to round down to take the value 1, okay, 1 through 9, shift it on to 0 through 8, divide by 3, multiply by 3, which is essentially the floor, and then add 1 back up to get us back into this silly base 1 setting. We do the same thing with columns. And now instead of 1 up to 4, we'll do row off plus 3. And the same thing with call off plus 3. So now we've actually iterated through the actual locations in this particular grid cell, I hope. And we're going to try to keep filter. So these are the RCs. Hopefully RC will not be a row equal to row and call. Actually, let's just if we deconstruct it into pairs, we have pairs of references, and it's just sort of annoying to compare pairs of references with pairs of yeah. I think this is largely correct. So we have now in this particular iterator. Actually, let's take this out to try to make this a bit more clear, because it's horrible. So we started with our range of row offsets here. We're turning each individual row into a 3 long thing. So we just get pairs of row and column at this point. Keep the, don't cross out the row and column, specific row and column that we have. And now, finally, map r comma c to be r comma c comma val. Oh boy. That's probably wrong. So this is a lot easier with a pencil, right? And you just draw a little square and work on it that way. So let's put all these together. Let exclusions be exclusions. Sorry, we have to give this a better name. Cell. Exclusions. Row.concat. Exclusions call. .concat. Exclusions cell. And we're gonna hit this with a distinct, because what we want to do is just have the distinct locations that we're gonna cross out, and then we will update inner by doing inner dot. What structure does inner have already? I bet we kind of want inner. Whatever. I think we should probably move this map up to here. Because this allows us, when we do this, to have row call as the structure that we iterate through, and indeed we're going to do this. If it has that structure, we can just do this. No, I lied. I'm such a liar. Yeah, let's not do that. I apologize. So it's val val row column. So let's do that again. I totally lied. I'm really sorry about that. But we are going to need to take these row and columns and vals. To that, need a format of val row col, so that we can. It remains distinct. We haven't changed the distinctness though. Actually, let's do that just to convince ourselves even more. All right, so this is now a little bit of logic that I assert does something non-trivial. Right? This is only the first rule that we have, where we cross out things that can't be possible, because we know that value is already present in a row, column, or cell. It's not the derivation rule that realizes that exactly one value is missing from a row, column, or grid cell. So, I'm trying to think. Let's try it out, I guess. See if it does anything. I mean, I'm sure it's not exactly going to build quite just yet, but we can see. What do we need to do? We should totally go and steal. Get Safari up here. Steal the SQLite with recursion example, because they had an example. Well, actually, they chose a really. I don't want to say it was a hard board necessarily, but they chose one that was meant to demonstrate guesswork. I have no idea if, we might as well just try this thing out and see if it imposes enough constraints that we actually get any derivations out. And if it actually required guessing, we might need to choose a simpler board. So what's the right way to do this? So we've got some text here, and we could just automatically read this thing, I think, probably, right? Like, if we turn this into it'll take a little work to remember how to use Rust's text iteration technology. But we could probably, let me delete that, because we definitely want to see the results. We don't have roots anymore, we just have, we have that start thing. So for count, comma. So I believe this is rows, row. So we'll count up. There should be hopefully 81 characters in here. Let's see if I have no idea what iter is going to do for us, but these are fortunately like bite-sized, and we don't have Unicode or any crud like that, so possibly this isn't too terrible. We're going to iterate through it, and we're going to call enumerate, which will tell us the position as we go. And I think all we need to do to get the row out and the column out is to do div 9 and a mod 9. So if we do let row equals count div 9, no, not just count div 9, but 1 plus count div 9, and let call equal 1 plus count mod 9. Right, so the columns are going to wrap more frequently. And we're going to want to do a start dot insert of val row call. And there's all sorts of things wrong here, sorry. And what we could do, if we want, I suppose we could we can close start here, and we can actually let's just not even bother. What this will do is when workers exit in timely data flow, they wind down their data flow, which means they close all their inputs, they run it to completion. This will hopefully tell us what's going on in this data flow graph. So let's check and see if this actually is even well formed. Probably not. Okay, this will take forever and a day as we. Oh no, sorry. We immediately discovered that there are bugs. Yeah. So need semicolons at the end of your stuff. Val, great. No method iter. Yeah, that seems right. Okay, how do we get through this nonsense then? I have to admit, one of the things I don't do a lot of work with is text processing in Rust. So we will need to bytes sounds great. How do we get bytes? Yeah, let's iterate over the bytes. And ooh, yeah. Sorry, we only want to do this for non-period things. So let's. I have no idea what it is, but let's type the following, and you can shame me. Hopefully Rust will yell at us, and by virtue of yelling at us, will drive us to the correct program. No. Okay, expected a U8, found a car, count, great, so this is what's the stupid, I don't even, well, let's see what's actually here. And then we'll try to figure out what we're actually looking at. We've got some other bugs to fix too. Type annotations needed, so the probe, okay, we don't actually know what timestamp type is going on here. We haven't talked about how we plan on changing the input, and because we just put a bunch of data in and then walk away. So we're just going to use the empty timestamp, which says, yeah, I don't really care. What do we have here? We probably need. I think anti-join is. Yeah. Okay. We need to do a very silly and annoying thing. Sorry. What we really want is set exclusion. And what anti-join does is it takes the first argument has to be key value structured, so we have vals, rows, and columns. And we need to do the following. Ready? Vals, rows, and columns, comma, empty thingy. And it's going to produce val, rows, and columns, and an empty thingy that we really don't care about. So hopefully that corrects that error. Yep. And now we need to not have a semicolon here. We need to actually return the iterator for flat map to work correctly. Oh boy. Okay. Probably just a whole lot of. Oh, I don't like that it says we don't use it. Oh yeah, no, we don't. That's a good point. Let's ignore all of these things for the moment. So we just need, I think most of our closures just need to have a move in them because they capture row, which is fine because row is a byte, so it's copy. But we need to give Rust permission to do that. And that's probably going to be pretty much everywhere. All right. Yeah. Cool. So let's run it. Yeah, that's terrible. Let's run it. And remember, we're just trying to figure out, because these are the hard parts of computer science, how to identify a period in a string. Like the whole, multi-dimensional incremental data flow computation part. That's the easy part. We're gonna go and build a thing that's gonna print some characters to us. At the very end, we expect to see. 7 and 9 aren't actually gonna be what we see because those aren't the bytes for 7 and 9, unless I greatly misunderstand how ASCII works. But we should see a whole bunch of the same byte over and over again, and we'll just look for that byte and ignore that byte. And I think we're going to have to subtract off the 0 character to get us down to, you'll see in just a moment. Maybe quite some moments. All right. So it looks like 46 is the thing we don't want to use. I wonder if we could have also done. Probably could have done that, right? I have no idea. Let's try that. We'll throw this in anyhow, just to check our knowledge. But we're going to have 46 here, and we're going to want this val here is actually a val minus, I believe. This is what we want. And actually, let's print out both of these things just to make sure to check our. Because there's nothing worse than doing this wrong and then spending a lot of time wondering why we were such failures. So I'll just take a little while to read, but no, my mistake. It's not gonna be fast. No implementation for U8 minus car. That's probably good. Probably we should have, pulled out individual characters and parsed them as integers and done a bunch of very safe things like that, which is reasonable, but yeah. So we have a few things that we don't use at the moment. I suppose we'll just clean these up while this is compiling, so that next time we try to do anything happens. The timer, yeah, I guess we'll just underscore for the moment. We are going to be interested in timing things, but it's not such a big deal. Reduce, we don't look at the key when we're determining which locations are determined, and that's good. This reduce thing, oh, neat. So these look like legit values, I think. What is it? 7, 9, yeah, good. 8, 5, brilliant. And you can sort of see now the data flow computation is often running. And let's see what activity monitor tells us about the amount of memory we're using. This is a debug build, so we might not be using that much memory because it takes quite a long time to actually get anything done. Here, sudo. Okay, we're actually not using very much memory at all. I wonder why that is. Usually in differential data flow, things just go sideways terribly almost immediately. Let's clean up some of these printy prints. Oops, we concluded that it was totally appropriate to use this test. Great. And what we can do actually, if we want, is throw an inspect down here at the bottom, which will allow us to inspect each of the VRC triples that go by. What we're not going to be able to tell, unfortunately, is, oh wait, yeah, hold on. Actually, oh well, let's do this. So we haven't actually put in all of the question marks, right? So what we really should have done for each of these dots, we should do a different thing, right? We should put in all of the values. We haven't done that. But having not done that, it's a little weird why we haven't reached fixed point. So before we do anything interesting, let's actually look and see what's going on down there. But this is where we should. Great. So let's see if we can get some insight. Mismatched types. Yeah, well, I put a semicolon there. That's wrong. So let's see what we can see. Slightly annoyingly, we're not going to be able to distinguish different rounds of iteration here. So that's probably just going to... I anticipate an utter disaster spraying out on the screen. Actually, I have another theory before we do anything. This is a naughty part of differential data flow, which is that if you have a data flow path from inner all the way down to the output that does not consolidate the data on it, so that it doesn't pause for a moment and make sure to cancel out positive and negative elements for the same value, it may run indefinitely just because it never actually gets around to saying, hold on, let's subtract these and make sure they're not just zero. And consolidate is the thing that does that. And in principle, like to make things nice and safe, we should probably put a consolidate on every iterate construct for you. We don't do that because it might be the case. Hey, look, we just finished. That's awesome. Is there a tab there? Oh, the tab is from this thing here. So we put in a bunch of stuff. We got a bunch of negative stuff. We should totally put the inspect after the consolidate. But yeah, actually, this looks like this might be, let's say, quotes working. Where working just means that we haven't. We took the initial state, and we just sat on it, which is good, good for us. And now that I think about it, actually, this shouldn't go off the rails because we're not actually doing any guessing yet. We're just taking a pile of constraints and reducing them down. And that pile of constraints might go down in size, but it's not going to get any bigger. And we're not introducing any constraints. Any possible values in this process. Yeah, so this looks pretty good. They're sorted, weirdly, they're sorted by value. So like 5 is the very first thing that we've seen. 9 is the very last thing. I think that's true. 5 and then 9, yep. But presented in a slightly weird order. Maybe we should do this row column value just for sanity of reading the results. Let's maybe do that later. But so let's write this code here now that is going to, in the case that we have a location that has one of these periods, meaning we don't know what the value is, we should totally get the row and column anyhow. And we should, for v in 1.10 start.insert v minus, okay, sorry, yeah. So that's, no, I screwed this up, I'm sure. Yeah. So this looks better. So this is just going to go through and say for 1 up through 9, if it's an unknown location, just put all the candidate values in there. Let's see what happens. Now, I don't actually want to look at all of those results, but let's do the following instead, where we are going to take these guesses, and we're just going to put them into row call form and do a count. So it's just going to count the number of values that exist. So let's do let initial equals start.map of val row call to row call. We don't even need to do, and we can do val. Since we know there's only one value for each value only occurs once, we really just need to count the number of times row and column show up here. We don't really care what the value is. That's an exciting optimization we can consider later. No, let's do it now, actually. Sorry, because I forgot how count works. Count doesn't want your silly value things there, it just wants to count the number of times these things happen there. So this should count for every row and column the number of distinct values there, which at this point, at the start, should either be 1 or 9 for pretty much everything. Now, afterwards, we should be able to do the same thing. Not really sure. Let's put these in slightly different order just to avoid mental. Don't mind me, just reformatting things. Our probe isn't actually being used yet, so it doesn't really matter where it is. But let's do the same thing here with oops, I guess final is a magic keyword, or at least this editor thinks it is. So let's not use that. Result dot count. So now we have these two things that are both row comma call and one count, a second count. Let's join them together. And what we should have, I hope, is row call count1, count2, and we will println this. This is dumb. It's just println the thing. All right. Does this work now? What do we need? A reference. We need a reference there. So the hope here. Oh, interesting. Yeah. Okay. That's. Sorry. I like tidying these things up because every time Rust tells me about these things, it's right and I'm wrong. And when I don't agree with it, it usually means that I have a bug. So I just like fixing them. What we're hoping to see with this inspect, the one that isn't showing us the candidates, is it's going to count for us the old and new number of candidates at each location, and we hope to see some reduction. I'm not sure we will. Actually, oh bother. There's going to be a lot of garbage that gets printed to the screen. If this works correctly, a lot of garbage that gets printed to the screen on account of printing out every iteration, all of the CRUD that goes past. Or the changes, at least, that go past. Actually, that's a good point. Like, if it really is just the changes and we really are reducing it, there should be a finite amount of stuff that goes past here. Right? We should see the initial content, and then every candidate gets removed at most once. And there's at most 9 cubed candidates, which is still more than we want to look at. I don't know, that is 81 times 9 is something large, 729 maybe. But yeah, so I do, this is like I think a good example of something that I often do a lot, which is that when you're working with larger data sets, it's not super helpful just to go and look at the data. You're not likely to see something particularly. Oof, tempted to subtract with overflow. I mean, I could believe that. That means we're still running a debug build first, but thank you for telling me that, Rust. Let's try to see where we subtracted with overflow. Sudoku line 70. Okay, that's not right. What the poop? Where is the actual? So line 70 is just telling us that this is the closure. Or this is, yeah, like in the drop code down here. None of this is helpful, is it? Is there better information, maybe? No. Worker thread 0 panicked at. You're panicking. 65. Oh yeah, well this is terrible. We shouldn't be subtracting. Yeah, why would we do that? It's ridiculous. We shouldn't do that. We actually had the legit numbers just right there. We should just use them, not characters. Thank you, Rust. Are we on battery power? I'm in an unpowered location at the moment. This is all like pirate radio, except sort of slow building data flow systems. These are debug builds, by the way, right? Yeah. So when we try to get around to doing release builds, it's gonna get a little worse. It's running. Sweet. So look at this. This looks great. Sorry, what are we looking at here? So each of these lines is saying for a location, row call, what was the initial count and what was the ultimate count. And what we're seeing is it's all ones, basically, which means, unfortunately, this is like a super easy problem. Super easy problem in the sense that just applying this one rule solves the Sudoku problem. and that's sort of boring. I'm gonna just comment out a bunch of the other random crap that we're printing stuff out. Though, I mean, we could see actually, I mean, like skim through and look. Yeah, I mean, we put in a whole bunch of different candidates out there. We definitely have a whole bunch of, actually, we're seeing this right down here. A whole bunch of 9s. I mean, sorry, I guess what I'm saying is it doesn't really look actually like 720 rows here when we start out. Is that wrong? No, sorry. I feel like, sorry for going quiet. I feel like, although we say we found 9 entries, if we look through and we say how many, what's the sum of all of this stuff that we saw here? Yeah, I mean, sorry, a possibility here is we haven't magically solved the problem. We've just written crappy logic that believes it solved the problem for us, and that might be utter nonsense. So, for example, 1, 3, we claim that there were initially 9 values and we got down to just 1, which means that we subtracted off, that we put in a whole bunch of 1, 3s in here. And this is where we really wish it was sorted by row and column first. But we put in, so this is the row and column part. We put in a 1, good for us. We put in a 2, good for us. We put in a 3, good for us. We put in a 4. Yeah, I mean, we're putting in all this stuff for this location. What's a different way we could think about this is if the number of periods that exists over here, 1, 2, we could just count them and print them too. These lists, their length for each value, they should contain each of the locations that there is a dot, and also each 4. So we should see, and we kind of do 1, 3, 1, 6, 1, 7, 1, 8, 1, 9. I guess that's it's not exactly what I'm expecting, actually. Sorry, take that back. Are we actually, so okay, it looks like we might be somehow screwing up something here. So the iteration, so for example, we would expect to see, I think, here, unless it just gets squished out really early. Yeah, interesting. Okay, sorry. So we're printing things out. We were printing things out at the end of the first application of this reasoning. So we've actually clobbered a lot of candidates already, which means that that's one of the reasons we're not really seeing a whole lot of output here. If we took this instead and put it at the beginning, let's rerun this. This should produce a slightly more epic amount of data. We will see the initial values of things, and because it's a fixed point, we'll still see all of the changes. So moving it from the end to the beginning isn't going to prevent us from seeing anything, but it does mean that instead of seeing only from after one step going forward, we'll see it from the sort of 0th step moving forward. And hopefully we'll convince ourselves that, like, oh yeah, we actually looked at all the data there. Actually, we can also check the result, because I think the SQLite thing has the actual result. Ta-da! So this is maybe, oh geez, we didn't consolidate it. Okay, so this goes far enough back that the buffer associated with VS Code has been exhausted. Let me. this VS Code terminal thing is really terrible. I mean, it may be my fault, but like if you paste things into it, it doesn't actually correctly pipe them around, and you get like 2 copies of various things. It's just not. Spent a while debugging that at one point. So, la-dee-doo-dee-dee. So what the SQLite folks are doing, by the way, is something, I mean, more complete, but also more exhausting here. What they're actually going to do is they're going to go through and write a recursive computation that in order finds the first position with a period, guesses all 9 values, and then takes any record that violates a constraint and drops it on the floor. So this entire thing is one record. So it's going to repeatedly rewrite strings, essentially, filling in guesses, and if it ever finds a contradiction, dropping it on the floor. Now, clearly, if you just took all of the periods and for each of them introduced all possible 9 values, it would grow massively, but at the very end you could throw all of the failures away. And in a sense, that's what they're doing, except they're doing that filtering as they go as well. But that's it's expensive. I mean, it seems like a sane thing to do, but the plan, at least for the work, was to get a bunch of negatives. I don't like that. So we start. We still. Sorry, I'm trying to think of why we. Oh, sorry. I take it back. Cancellations are an inherent part of. Okay, so in the first iteration, we see some data. In the second iteration, okay, now we start deleting things, basically. So it's actually legit that we see retractions. I mean, to be honest, this is like a totally plausible amount of data going past. And the timestamp, oh, wonderful. The timestamp is telling us in which round of iteration it was. So we did 10 rounds of iteration. Looks like we got down to a correct answer. We can, since we have rows and columns here, we can go through and print out for each row and column. So we can do like a reduce and print out the values for each. Let's do that. Let's stop printing out all this horrible nonsense just because it's very wordy. So let's see. Instead of doing a count here, so we have beforehand the initial count, and really all this is telling us is it was the count 1 or was the count 9. Let's instead do this afterwards. Take a result, turn it around so it's got a row and a column and a value, and do a reduce where we have our key that we're not going to look at. We're going to have an input and an output, and all that we're going to do is build up a vec containing each of the inputs. So we're going to list all of the values. And instead of the number 1, we're going to see a list, and ideally that list will have, we sort of know it already, but it'll have single elements, and it would tell us all of the candidates otherwise. So all we're doing here is we're just building a vector containing the values from input, not their weights, because we think those are all 1. And then we're going to put that into the output, and we will do our join again. We're going to inspect it, and let's maybe print something a little bit more tasteful now. So we've got four things to print out. We're going to say row, call, init, and vals. And init is basically just telling us was this a question mark to begin with, or or not, and vals is listing all the values. And we need to correct our bugs. We're actually using val now, that's great to know. Expected a tuple with 3 elements, found one with 2 elements. What? Oh, is that really how join works? Wait. I expected a key val pair. Is that not what join produces? Sorry, this is just a brief. There's like 12 meanings of join in, unfortunately, in math, and no, it should produce a key, a pair of things, key and a pair of values, not a triple. So what's the complaint? Expected a tuple with 3 elements. Why did you expect a tuple with 3 elements? I don't know, maybe because I haven't fixed that previous bug yet. Okay, so we pushed in a reference to a thing. Let's see if maybe this works better. Okay, it's quite certain that we're trying to present references to U8s, not U8s. All right, good. Well, we cleaned that up just with enough stars. I don't know why this is a ref to a ref to U8, but oh, maybe this iterator is but yeah, it's a reference iterator, and these are references inside. Okay, that makes sense. It is a reference to a reference. Expected a tuple with 3 elements, found one with 2 elements. This is a less helpful error message. Oh, sorry, it was actually telling us exactly what the problem is. So I see, inspect is actually showing us all of the different timely fields. So we're getting the data as well as the time, which is empty, and the change. Which will probably be +1 for all these things, but if we started changing the data around, it would be could go negative. So right, if we I suppose if we add constraints, we would see some negations in there, because that would remove some of the candidates potentially. But actually, if we get, if we see this actually running promptly and producing correct-ish looking answers that sort of match what SQLite is telling us the correct answer should be, that'd be great. We could pause here and eventually do the next rule a little later on, and potentially do the backtracking version even later on. Though to be honest, for the backtracking, I was largely just going to steal the structure of the algorithm that SQLite had there, where instead of starting with all possible 9 values for every question mark, this first step is actually reduced down the space of candidates a fair bit. So yeah, well, okay, so here's a bunch of candidate results. Let's see, 5, 3, 4, 6, 7. Let's see if that looks similar at all to 5, 3, 4, 6, 7, 8, 9, 1, 2, 8, 9, 1, 2. Yeah, it looks good. How about at the very end? 3, 4, 5, 2. 3, 4, 5, 2. I don't know. It's looking pretty good. Like, I think we did it right. Let's do a release thing here. And the release build is going to take a little while. It's going to take a certain amount of battery power. But we can then run it and see if it goes relatively fast. I mean, it didn't look like it took very much time, to be honest, even the debug build. And we haven't been particularly attentive to performance here. I mean, you know, a lot of the stuff is not insane. Like the reduce is, you know, a bit crazy. Like we're keeping all these values around. All we really wanted to know is the count equal to 1? So we definitely don't need to do all that work. This is more of a do a count, and if the count equals 1. So counts are more efficient than keeping all these values. But basically, this is an expensive operator when there are lots of choices, and we don't need to do all the work when there are lots of choices because we don't really care about that case. We care about the case where there's exactly 1, so we should figure out where there's exactly 1 efficiently, and then pick out those locations. It's sort of more obvious if there were like a million different values you might have. You know, quickly figure out which are the keys that you care about, and then leap. You know, use that and a join to leap immediately to those keys and their singleton values. That's probably not what's holding up the show here, but yeah, nothing super obvious. This distinct, I think, is kind of mandatory. Concat is like all these concats and flat maps and stuff like that are, I mean, not free, but they're stateless linear operators that only do work proportional to the changes that flow through them. You know, anti-join isn't for free. It's a join. In principle, the result of distinct, like we could take the state that lives there and reuse it in the anti-join. That's a bit of an exotic transformation to do. I mean, it's cute, but it's yeah. Yeah, I mean, in principle, like we could actually pack all of this stuff, all these exclusions up into this reduce. So whether we want to or not is an interesting question. But like, you know, basically what this says is like, haha, we've found input length is equal 1. We found something that should cross out a bunch of other locations. That seems like a fine time to actually go and announce each of those locations rather than, I don't know, like this isn't terrible, but you know, building new data flow to do each of the 3 different types. Nothing good is happening here, right? We're not shuffling the data around or using data parallelism or any of that junk. We're literally, you know, just chaining some function calls onto some data somewhere else. If you put these together, the compiler could optimize them. But if you put them in the same closure, the compiler could optimize them together. And by having them be separate data flow stages, the compiler isn't going to be smart enough to see that. So we're compiling, and yeah, we're almost there. But this is the trade-off: is that you might get a faster Sudoku solver with a release build, but differential data flow seems to really cause Rust and LLVM to struggle a bit. I'd love to learn more about how to fix that. How do you structure your programs in a way that doesn't cause? Let's look at activity monitor over here. Yeah, well, apparently load is sufficiently high that activity monitor is not. There we go. So Rust is hard at work, and it's not actually using all that much memory. I don't know. Who knows what it's doing? But it's doing a lot of it. These are the really thrilling moments. I don't have lots of really clever idle conversation to make at the moment. I got an off-color joke from my mom, but I'm not going to report that. But it was funny. Yeah, I'm not sure if you can hear this, but the thing that I listen for when I'm building is that at some point the fan starts going down, and that's because Rust has finally gotten to a point at the very end where everything's nice and single-threaded, and it's just about done. And that's when I start to get excited, is when the pitch of the fan drops a little bit, and I start to pay attention. Like, ooh, I might get some code to run. I mean, the good thing is this part of the video will compress really nicely. You don't have to have downloaded very much to get all of this content. I've just noticed, and it's really winding me up now that I see it, that all these things are indented one level too far. And if I unindent them, we're going to have to rebuild this stupid thing, because although it's not a semantically meaningful change, Rust will struggle to understand that, I believe. I suppose. No, I guess this stuff is also indented too far. Yeah. Yep. Never mind. This is what I've been reduced to. Hopefully we'll survive. I mean, we might run out of juice before... Ooh, where is Rust, actually? Part of this is the recorder that's going on. Oh, is Rust done? Rust is done! Oh my goodness. Rust finished. I cleared the... I'm really sorry. I cleared the buffer, so we can't actually see how long it took to run. But, sweet. So that took... I don't even know what this means. Apparently, something like 100 milliseconds, I think is what it's saying. Though, like, no one really wants to. No, I guess between the user and system, it's something like 100 milliseconds, which is cool. The SQLite people are really excited that they cleared 300 milliseconds on a modern workstation. I mean, we probably took 10 minutes plus 100 milliseconds. And we got the building and the... we also solved a simpler problem than they solved. They did all this recursive guessing stuff, building up lots and lots of... Actually, sorry, we don't actually know how many candidates they built up, because this is apparently a pretty constrained problem, since just this one type of inference, like backtracking isn't actually required. So it might be that a backtracking algorithm actually does really well in this setting, because it really quickly finds these contradictions and calls its set of configurations that it's maintaining. But I'm going to stop here for now. I'm probably going to try to pick this up again and write, find some slightly harder Sudoku problems. Write, let's see, at least the other inference rule that says if all but one value are present in a row, column, or 3x3 cell, that determines that value. That will unblock slightly harder problems. And we should also be able to do the backtracking solver at the end of it. But for now, I'm going to stop. Thanks for watching, and I hope you learned something, or at least maybe got a little stimulated about how you might use exciting data parallel data flow to do something that probably has a much simpler solution in your programming language of choice. Cheers.